what is a Taylor series? Well, a Taylor series is a way to write a function as an infinite sum of polynomial terms based on the function's derivative at one point. So what is that? Well, over here I've drawn a random function, and I'm going to try to approximate this function by using one polynomial and then adding more polynomial terms to that. So if we could have a polynomial of just one term, right, we at least want to create the first polynomial so that it matches the value of the function at x equals 0. So we would have something like this, p of 0, and p just stands for polynomial, the polynomial that I'm going to construct here, equals f of 0. Now the simplest way to make this happen is to choose a constant polynomial that takes the value of f of 0 everywhere. All right, so we can just write p of x equals f of 0. Now, if I were to graph this, it would look something like this. It would just be a horizontal line. This right over here is the same thing as something you might have seen before, the standard y equals b. In fact, it is the same thing, it's just written differently. So now you might say, okay, well, this horizontal line is a pretty terrible approximation of this function, right? It only approximates the function at this one point, but it's really bad everywhere else. It does a terrible job of approximating this actual function. But, hey, it was just one polynomial term, and obviously we expect it to be a pretty bad approximation. All right, so we know that p of 0 equaling f of 0 makes our polynomial touch the function at this one point. But now we want a more accurate approximation. So what are we going to do about this? So what we're going to do is we're going to add some more conditions. We want p prime of 0 to equal f prime of 0. P prime of 0 to equal f prime of 0. This means that now the polynomial is not only going to touch the function at this one point, but it's going to have the same slope. It points in the same direction, so that's going to be a closer approximation. So what we're going to have is we're going to have p of x equals f of 0 plus f prime of 0 x. So right here, f prime of 0 times x is just the slope times how far we've moved from 0. So what's cool about this new polynomial is that it not only equals our function at x equals 0, but it also has the same first derivative, meaning that our polynomial and our actual function will have the same slope at x equals 0. So this is going to look something like this. Something like that, a tangent line. So if making sure that the polynomial and the function have the same first derivative at 0 gives us a closer approximation, because we can look at this approximation and say, hey, yeah, that looks a little bit closer, right? It approximates it more accurately. It's still not very good, right? But it's better than the original. So if making sure that the first derivatives were the same give us a closer approximation, maybe we can get an even better approximation by making sure that they have the same second derivative. So what we're going to do is we're going to add some more conditions. P double prime of 0 equals f double prime of 0. So now we want the polynomial's second derivative to equal the function's second derivative. Right, so this would be p of x equals f of 0 plus f prime of 0 x plus f double prime of 0 times 1/2 times x squared. Up to now, our polynomial only had a constant term right here and a linear term. But when you take the second derivative of those, they both disappear. The constant term goes to 0, and the linear term also goes to 0. So without going too much into the math of it, all you need to understand now is that we want the second derivative of our polynomial to actually equal the second derivative of the function. And so in order to do that, we need to add a term that survives when we take the second derivative. The simplest thing to do is to add an x squared term. But when you take the second derivative of x squared, you get a factor of 2, and that's why we divide by 2. In order to make the results exactly f double prime of 0, we have to divide by 2. And that's why we have this term right over here with all the 1/2 and x squareds. So by adding this term to our polynomial value is not only the same thing as our function at 0, its derivative at 0 is the same thing as a derivative of the function at 0, and its second derivative at 0 is the same thing as a second derivative of the function at 0. So there's a pattern here. Our polynomial not only matches the value of the function at 0 and the slope at 0, but it also matches the curvature at 0. So we would get something like this. Alright, so you might say, hey, that's actually a pretty good approximation. It's a closer approximation. It's not super accurate, but it's a closer approximation than the previous approximations. And you might guess the more terms we continue adding, the closer and closer approximation we will get. In theory, if we do this infinitely, adding an infinite amount of polynomial terms, all of the derivatives should be the same, and the polynomial will pretty much equal the function. So if we had a lot of time on our hands, we could write p of x equals f of 0 plus f prime of 0 x plus f double prime of 0 times 1/2 times x squared plus f prime 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 of 0 times 1/3 times 2 times x to the third power plus f prime 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 of 0 times 1 divided by 4 times 3 times 2 times x to the fourth power. So you can keep adding terms to where your nth term would be the nth derivative of your function evaluated at 0 multiplied by x to the nth divided by n factorial. And notice, this right over here is the same thing as 4 factorial. This right over here is the same thing as 3 factorial. This is the same as 2 factorial, and even though it's not here, that's the same thing as 1 factorial. So our polynomial evaluated at 0 not only matches the value of the function at 0, it matches the slope at 0, the curvature at 0, the rate of change of curvature. As we keep going, the rate of change of the curvature, sometimes called the snap, and we keep on going, getting a closer and closer approximation until we, in theory, get the exact value of the function. So by adding this fourth derivative, right, instead we might get something that looks like this, right, a closer approximation. And as we keep adding terms, we might get closer and closer and closer until we eventually get the exact function. So what I have set up over here is called the Maclaurin series. It's a special case of the Taylor series where you expand the function around 0 instead of another point. So when you have a Taylor series, you can pick any center point. But in this Maclaurin series, we center it around 0. So in the next video, we're going to do this with some actual functions, just so that it makes more sense. So I hope this video was helpful. I hope you got the main concept, the theory of what the Taylor series is. I'll see you in the next video, and as always, stay positive.